In this module, we will discuss one of the assumptions of a linear model, that is the normality of errors. What we specifically will discuss is what happens when we do not have normality of errors, what problems we encounter, or what are the properties of the Ols estimates of the parameters when we assume normality of the error terms in a linear model. In this module, we are discussing the non-normal errors. We know that certain assumptions are made when fitting a linear model to a data set. One of them is the normality of the error terms. In this module, we will discuss what the normality assumption of the error does, how it influences the estimation of the parameters, and what are the effects of non-normal errors. We will also see how we can consider a linear model of the form y equals x beta plus u. This is a very standard form of a linear model where y is our dependent variable, x is the matrix of independent variables, beta is the vector of parameters, plus u is the error term. The parameter vector of the above model is beta, and it contains as many parameters as the number of independent variables that we are using plus the one parameter for intercept. Now the components of the parameter vectors are estimated by the method of ordinary least square, and this is when we have a linear model that satisfies all the assumptions that are made. The assumptions that the error term u have expected value 0 and they have a constant variance, that is, they are homoscedastic, and we also assume that the error terms are uncorrelated, which means there is no autocorrelation. The Ols estimates, or the ordinary least square estimates of the parameters thus obtained from a linear model which satisfies all the assumptions, are called unbiased, and they are also of the minimum variance. That is, if we have a class of estimates for these parameters, the Ols estimates will have minimum variance among all of these estimates. Now, if we wish to perform testing of hypotheses about the parameters, knowing the sampling distribution of the errors is of utmost importance, and we will see later on how the sampling distribution of the error term comes in handy when performing testing of hypotheses. The regression parameters are linear functions of the error terms. We have seen in the modules before how we can write the regression parameters beta naught, beta 1 and so on in terms of the error terms or as linear functions of these error terms. So, an assumption about the sampling distribution of the error term is always useful when we want to discuss the sampling distribution of the regression parameters. So, the errors are said to be normally distributed under normal situation. If they are not, then we would like to make some adjustments or some changes so that we can restore the normality of these errors. Now, according to the classical assumption of linear regression, we assume the error terms are ui and they are distributed normally with a mean 0, that is expected value of ui equals 0. Variance is sigma square for every error term, or in other words, the error terms are homoscedastic. Since we have assumed that the mean value or the expectation ui equals 0, we assume that variance of ui, or in other words, expected value of square of ui equals sigma square. And we also assume that the covariance between ui and uj, that is expected value of ui and uj, that equals 0 for I naught equals j. Covariance of ui uj 0 asserts that the assumption of autocorrelation or assumption of no autocorrelation between serial error terms are 0. Now, why do we need the normality assumption? Let us elaborate on this question. The error terms in a regression model represents a combined influence on the dependent variable of a large number of independent variables. If you remember the regression model, suppose a multiple regression, it was written as y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta p xp plus ut, where ut was the error term. Now, if we turn these terms around, we can write ut as yt minus beta naught minus beta 1 x1 minus beta 2 x2 minus beta p xp. So, the error term is nothing but the combined influence of the independent variable on the dependent variable y. We take the difference between yi, which is the observed dependent variable, and from this we subtract the expected value of the dependent variable given the values of independent variable. This is given by beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp. And if you look at these terms, ui is nothing but the difference of the observed and the expected value of our dependent variable. So now the influence of these independent variables on our dependent variable y is random. By the famous central limit theorem, we know that if the number of these independent and identical variables is very large, then their sum is normally distributed as the number of variables increase indefinitely. This provides us with a justification for the assumption of normality of ui. Now, if we look at a variation of the central limit theorem, that also states that even if the number of variables is not very large, or if they are not even independent, then the sum is still normally distributed. So, one of the useful properties of the normally distributed random variable is that their linear combination also follows a normal distribution, but with appropriate parameters. The least square estimates of the regression coefficients, beta naught hat and beta 1 hat, being linear combination of the error terms, are also normally distributed. As I had pointed out before, the regression coefficients involved in a regression model, they can be written as linear functions of the error term. Now, since the error terms are assumed to be normal, then in that case any linear function of these normally distributed error terms is also normal. So, beta naught hat and beta 1 hat, being linear combinations, are also assumed to be normally distributed with appropriate parameters. Also, a normal distribution is comparatively simple. Normal distribution is one of the most commonly used statistical distribution, and the properties of this distribution are also well studied and they are quite easy to follow. So, assuming a normal distribution for the errors is comparatively makes study of the errors simple, and also since the normal distribution is defined by only two parameters, it is easy to handle. Now, when we assume normality, there are certain properties that the ordinary least square estimates of the regression parameters satisfy. What are these properties? Let us look at these properties of the Ols estimators under normality assumption in detail. First of all, the estimates for the parameters are unbiased under a normality assumption. Second, they are efficient. When I say they are efficient, it means that they have minimum variance among the class of all estimators. So, taken together with property 1, the ordinary least square estimators are minimum variance unbiased estimators, or most efficient estimators in other words. Third, the estimators which we obtain for the regression parameters under the normality assumption are consistent. That is, with the increase in the sample size, the estimators approach the true population values. The intercept parameter, which is beta naught, this is distributed normally under the normality assumption of the error terms. As I have mentioned before, the intercept term beta naught and the slope parameter beta 1 in a single regression model, they can be written as linear functions of the error terms. So, if the error term is assumed to be normal, then the intercept parameter is also distributed normally. And since normal distribution is defined by two parameters, the mean and variance, we have the mean and variance written here for the distribution of beta naught. For beta naught, the mean of the normal distribution is beta naught, that is expected value of beta naught hat equals beta naught, and the variance for beta naught hat, the estimate of beta naught, is given by summation xi square divided by n times summation xi square times sigma square. Or more compactly, we can write beta naught hat follows a normal distribution with mean beta naught and variance sigma square subscript beta naught hat. The slope parameter, which is beta 1, this also being a linear combination of the error term, is distributed normally. And for this normal distribution, the mean is expected value of beta 1 hat equals beta 1, and the variance of sigma square beta 1 hat equals sigma square divided by summation xi square. Or more compactly, we can write beta 1 hat follows a normal distribution with mean beta 1 and variance sigma square on subscript beta 1 hat. Now, continued with the properties of Ols estimators, another property of the Ols estimator of the estimate of variance of the error terms, that is sigma square, that is n minus 2 times sigma square hat divided by sigma square, is said to be distributed as a chi-square distribution with n minus 2 degrees of freedom. So beta naught hat and beta 1 hat are distributed independently of sigma square hat. Beta naught and beta 1 have minimum variance in the entire class of unbiased estimators, and that is why beta naught hat and beta 1 hat are called the unbiased minimum variance unbiased estimators, or the most efficient estimators of beta naught and beta 1, because we know that they follow a normal distribution, and when the normality assumption is satisfied, then we have most efficient estimates for the unknown parameters. This property is very useful because unlike the Gauss-Markov theorem, it is not restricted to the class of linear estimator only. In case of Gauss-Markov theorem, we have seen before, we only spoke about the linear estimators or functions of linear estimators. But in this case, in general, we can have any estimator which will have a minimum variance. Now, when we talk about non-normality of the errors, there are certain situations where the normality assumption of the error, it is violated. If it is violated, then we would want to detect it before fitting a model, and in order to detect this, we would have to use some tests. There are a number of tests available that we can perform to test normality of the error terms, but here in this module we will just discuss a couple of these. One is the chi-squared goodness of fit test, the other is the Jark-Bera test of normality. So let us first look at the chi-squared goodness of fit test. In this test, let me walk you through the steps that are involved. We first, in the first step, fit a regression model to the given data and we obtain the residuals. We simply fit a regression model to the data using the method of least square, and from the obtained model we get the residuals ui hat, or in other terms, the estimated errors. Once we have the estimated errors or the residuals ui hat, we also compute the corresponding sample standard deviation for ui hat. The residuals are then ranked and put into several groups, depending on how many standard deviations they are below or above 0. The mean is assumed to be 0 for the residuals, and thus we count the number of standard deviation each of these residuals are below or above the standard deviation for the distribution. Let me consider the following data. Here we have a set of observed residuals denoted by OI, and we have a set of expected residuals denoted by EI, and the last row of this table gives us the values of OI minus EI whole square divided by EI. So in the chi-square goodness of fit test for the above data set, the row marked observed residual gives us the frequency distribution of the residuals for specified standard deviations above and below 0. And the entries in the expected residual, they give us the frequency distribution of the residuals based on the hypothesized distribution. In this case, it is normal. Thus, we have a set of observed residuals which we actually get after fitting a regression model and obtaining the residuals. And then we have the expected residuals. Since we are testing the assumption that there is normality of the errors, so the expected residuals column, that gives us the frequency distribution for the assumed or the hypothesized distribution, which is normal in this case. Using the observed and expected frequencies, we get the chi-square test statistic. If the reader remembers, for a chi-square test of goodness of fit, the test statistic is given by summation over I equals 1 to n, where n is the number of observations. We have OI minus EI square divided by EI. So for each of these cases, each of these observations, we take the observed frequencies. From this we subtract the expected frequency. We take the square of this difference and divide it by the expected frequency. So here we have done the same. If you go back to the previous table, we have observed residuals, we have expected residuals, and we have observed minus expected square divided by expected residuals. And just taking the sum of all of these will give me the chi-square test statistic value. So in order to carry out the testing of hypotheses, we assume a chi-square distribution of the test statistic with n minus 1 degrees of freedom. Here n minus 1 is the degrees of freedom for the chi-square distribution. N is the number of classes in the frequency distribution. In our case, n is 6. So the degrees of freedom for the chi-square test that we need to perform the test of goodness of fit is 5. So we perform the testing of hypotheses using the chi-square test statistic and get the chi-square critical value from the table using the degrees of freedom 5 and any chosen level of significance. Once we get the critical value, we compare it with our calculated value of the chi-square test statistic. So we perform the testing of hypotheses by comparing the test statistic value and the critical value, and we reject or not reject accordingly the null hypotheses depending on whether the chi-square test statistic value is greater than or less than the critical value. Now the next test which we use to test for normality is the Jar-Bera test of normality. In this test for normality, we assume asymptotic or large samples. In case of this test, we assume that the sample size or the number of observations that we have is greater than or equals 30, which is effectively considered as a large sample. So we assume a large sample to perform this test. This test is again based on residuals from the ordinary least squares estimates of the parameters, just like the chi-square test. So just like in chi-square, the first step was fitting a regression model using the method of ordinary least square and then obtaining the estimated residuals. We do the same thing here. In this test, we first obtain the residuals, and then instead of computing the standard errors for these estimated residuals, we compute the measures of skewness and kurtosis of the residuals. After we compute the measures of skewness and kurtosis, denoted by S and K respectively, we can now calculate the test statistic value. The Jar-Bera test of normality has a test statistic which is given by JB equals n times S squared divided by 6 plus K minus 3 squared divided by 24. Where, as I mentioned before, S represents the skewness and K represents the kurtosis. So we know that for a normal distribution, the value of skewness is 0 and the value of kurtosis is 3. So K minus 3 in the test statistic represents the excess kurtosis present. Under the null hypothesis, the residuals are normally distributed, and the test statistic JB follows a chi-square distribution with 2 degrees of freedom. If the p-value of this test is very low, we reject the null hypothesis. Now, as you can see in this test statistic, we have JB equals n times s squared divided by 6 plus k minus 3 squared divided by 24. Now, if the errors are actually distributed as normal, then s should be 0 and so should be k minus 3. Thus, JB should take the value 0 or very close to 0. So, as the distribution of the error terms is deviated from normal, in other words, if it follows any other distribution but normal, then the value of this JB statistic will be different from 0, as the value of this test statistics gets bigger and bigger, and if this value gets greater than the critical value from the chi-square with 2 degrees of freedom, we reject the null hypothesis that the errors are normally distributed. Now let us look at a summary for the non-normal errors. Without the normality assumption of the error terms, under the other assumptions, the Gauss-Markov theorem shows that the Ols estimators are blue. So even if we violate the assumption of normality of the error terms, if all the other assumptions of Gauss-Markov theorem, that is no autocorrelation, homoscedasticity and absence of multicollinearity in the data, if these assumptions are satisfied, then the ordinary least square estimators for the parameters are still best linear unbiased estimators of the unknown parameters. Now, if we consider the normality of error terms in addition to the other assumptions of the Gauss-Markov theorem, then the Ols estimators of the parameters are not only best linear unbiased estimator of the slope and intercept, but also follow a normal distribution themselves. As we have seen before, the normal distribution of the error term also ensures a normal distribution for the slope and intercept parameter because they are linear functions of the error. The distribution of the variance of the error term is chi-square if we assume the normality of error term, because chi-square again is derived from the normal distribution. To be specific, the square of standard normal variables and taking the sum of the square of standard normal variables, we arrive at a chi-square variable. So, the variance, if we assume normality of the error, would have a chi-square distribution. An alternative to the method of least square is the method of maximum likelihood to get the estimates of the unknown parameters. In this method, we obtain the estimates of the parameters which maximize the value of the likelihood. Just like in case of least square, we obtain the estimates which minimize the square of the errors. But to use the maximum likelihood technique, we must make an assumption about the distribution of the disturbance or the error term. So, under the normality assumption, because we have a concrete distribution for these errors, the maximum likelihood and the least square estimates can both be used, and the estimates in both the cases for the intercept and the slope parameter are identical. So, although the maximum likelihood and the least square estimates of the variance of the error terms are different, in case of large samples, they are again identical. So, in this module, we have looked at the normality of errors. We have looked at this assumption from the perspective of estimates of the parameters that we obtain using the ordinary least square method. We have seen how the assumption of normality about the error influences the distribution or the sampling distribution of the slope and the intercept terms in our regression, and how the non-normality of error estimates influences the estimation process of the least square for the unknown population parameters.